Hi viewers, in this video we will solve problem 8.27 from the book Heat Transfer J.P.Holman 10th edition. Here is the statement of the problem 27. A square room 3 by 3 meter has a floor heated to 300 Kelvin, a ceiling at 290 Kelvin, and walls that are assumed perfectly insulated. The height of the room is 2.5 meter. The emissivity of all surfaces is 0.8. Using the network method, find the net interchange between floor and ceiling and the wall temperature. Okay, so this statement has given some data. So first we will write that and then we will proceed to solution. The temperature T1, let's say this is temperature T1, that is at 300 Kelvin. Temperature T2, it is this is the floor temperature and is the ceiling temperatures, and the wall temperature we need to find, that is T3, let's say, and the net heat transfer between the floor and the ceiling, that is 1 to 2. That is also our need to find. The emissivity of the surface 1 and 2, that is equal, and it is 0.8. So this is, let's say, the ceiling, this is the floor. The temperature of the floor is T1 and the temperature of the ceiling, that is T2. So it is at a higher temperature, it is at a lower temperature. And the temperatures of the valve, here is the valve, this is, let's say, T3. So the dimensions of the floor, that is X, here it is Y, and the distance between these floor and ceiling, that is D, capital D, and it is 2.5 meter in height. Why these dimensions are necessary? Because with the help of these dimensions x, y, and d ratio, we can calculate the shape factors between the floor and ceiling. Okay, so what is x? That is 3 meter. Y, that is also 3 meter. And d, capital D, the distance between the floor and the ceiling, that is 2.5 meter. Okay, x by d ratio, that is 3 divided by 2.5, we will get its value, that is 1.2. And y by d ratio, that is also you will get 1.2. So x by d ratio is on the x-axis of this graph, so it will lie here. So this is x by d ratio. Now look at this curve. If you find the curve for 1.2, it will be between 1.5 and 1. So the curve will be in between 1 and 1.5 curves for y by d ratio. So for y by d ratio curve, that will be in between of 1.5 and 1 line curve. So if you intersect this x by d ratio with y by d ratio, it will coincide at this point, because the curve for y by d ratio will be in between 1.5 and 1. So here the corresponding shape vector between these surfaces will be 0.25. So here you can see from the graph, So here I can say that the shape factor between these two surfaces, between the floor and the ceiling, that is 0.25. Summation rules, I can also say that f of 1 1 plus f of 1 2 plus f of 1 3 is equal to 1. So for flat surface, f of 1 1 will be 0, f of 1 2 is 0.25 plus f of 1 3 is equal to 1. So if we subtract 0.25 from 1, you will get shape factor for 1 to 3, that is 1 minus 0.25, that is 0.75. Okay, the area A1 and A2, that is same, and it is 3 cross 3, and that is 9 meter square. So by reciprocity theorem, I can also say that A1 f of 1 3 is equal to A2 f of 2 3 is same, because this area A1 and A2 is same, it will be cancelled out, and that is equal to 0.75. So the shape factor f2 to 3 is equal to f1 3, and it is 0.75. Okay, emissive power of the surface 1 is equal to sigma T1 to the power 4, that is 5.67 multiplied by 10 to the power minus 8 multiplied by T1, that is 300, all to the power 4. You will get its value after simplification, that is 459 watt per meter square. So from this graph we have taken the shape factors f of 1 2 and its corresponding shape factors that is required in order to solve this problem. So in further this problem, this graph has no need, so I am now removing it from the display. Okay, here I will draw the resistance network diagram for this surfaces that is provided in the statement. So first the emissive power of the body 1, then its surface resistance, then its radiosity J1, then again the space resistance between the radiosity J1 and J2 the body, and then its surface resistance of the body 2, and its emissive power EB2, and this is EB1 J1 J2. So here this is the valve. It is perfectly insulated, so its surface resistance is 0, so in that case J3 is become EB3. So the radiosity of the body B1, the ceiling, and the valve, so this is J2 and J3. This resistance is equal to 1 minus E1 divided by A1 E1. This is 1 divided by A1 f of 1 2. This is 1 minus E2 divided by A2 and E2. This is resistance is equal to 1 divided by A2 f of 2 E, and this resistance is equal to 1 divided by A1 f of 1 3. F of 1 3 and f of 2 3 is equal with each other because of the reciprocity theorem. So let's say this is resistance R1, this is resistance R2, this is resistance R3, R4, and this is resistance R5. Now first we will solve the resistance values, each resistance value, and then we'll move forwards for its solutions. So let's solve it. So resistance R1 is equal to 1 minus emissivity 1 divided by A1 E1. So it is 1 minus 0.8 divided by 9 multiplied by 0.8. So we get its value, that is 0.0278. R4 is equal to R5 and it is 0.148. Because A2 is equal to A1, f of 1 3 is equal to f of 2 3, so that's why R4 is equal to R5. Now consider the resistance in this triangle. So first we will focus on the resistance that are in triangle shape, and we will find its net resistance, equivalent resistance, and that equivalent resistance will be in series of R1 and R3. So look at here, just we have picked the resistance that are in triangle shape. So this is J1 node and this is J2 node. So from 1 to 2 node, if you look at this resistance network, the resistance R5 and R4 are in series with each other. So its net resistance, that is R6, is the sum of the R5 plus R4. I can say that R6 is equal to what is R5 and R4, and then the R5 and R4 are equal, so I can say it is 0.148 plus 0.148, because both of these resistance are equal with each other. So you will get the R6 value, that is 0.296. Now the equivalent of R5 and R4 resistance that are in series with each other. Now the resistance R2 and R6 are in parallel with each other. So its equivalent resistance is, let's say, R7. So 1 over R7 is equal to 1 over R6 plus 1 over R of this whole triangle. The resistance that are in triangle shape, its equivalent resistance is R7. You will get its value, that is 0.177. So in terms of this resistance R2, R5, R7, I can say that this R2, R5, and R4 resistance are equivalent to R7. So I can say that the total resistance of this heat transfer network is the sum of R1 plus R7 plus R. So the total resistance R2, that is equal to R1 plus R7 plus R3. So after additions, you will get the total resistance of this heat transfer between floor and ceiling, that is 0.2326. Okay, so the heat transfer between these two surfaces, between from the floor to the ceiling, that is 1 to 2, it is equal to AB1 minus AB2 divided by the total resistance that comes across to the heat transfer, that is R2 RT. Sorry, so AB1, that is is we need to find the temperatures of the valve. So if you look at this resistance network diagram, so from its geometric symmetry, I can say that J3 is equal to AB3, that will be equal to half of the AB1 plus AB2 value. So half of the, what is AB1? That is 459 plus 401. So after simplification, you will get 430 watt per meter square. I can also say that EB3, that is emissive power of the valve, that is perfectly insulated, that is equal to sigma T to the power 4. Very interesting to find the temperatures of the valve. So I can say that 3 to the power 4 of the valve, that is perfect insulated, that is 295.1 Kelvin. And this is the temperatures of the valve, that is perfectly insulated. And this is the final answers or statement. I hope you understand. If you still have any confusion, you can ask in the comment section. Please do subscribe my channel if you haven't subscribed yet, and share with your friends. Thank you so much.